இல்ல இதாயிட்டு இருக்கு, நம்ம பேசலாம் கேட்டுட்டு இருக்கிறது ஸ்பீக்கிங்.
சரவணன் சார்.
சார்
சார் லைன்ல இருக்கீங்களா?
இருக்கு
சார். இப்போதைக்கு பார்ட்டிசிபென்ட் 79 பேர் ஜாயின் பண்ணிருக்காங்களே சார்.
79 சார். அலோ கொடுக்கலாமா? நிறைய பேர் வெயிட்டிங்ல
இல்ல 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 வேணாம் வேணாம் வேணாம். இப்போ நம்ம ஒன்னும் ஸ்பீக்கர் வரலையே.
சார்.
ஒரு நிமிஷம் சார். உங்களுக்கு இது பண்றேன் சார். கூட்டு மீட்டிங்ல சார் நீங்க ஓகே ஓகே ஒரு ஆமா சார். அதுதான் சார்.
சார் வரலையே. என்ன கொடுத்தாச்சு.
இல்ல இப்ப திருப்பி இது பண்ணுங்க சார். அதே லிங்க் தான் சார். சேம் லிங்க் தான் திருப்பி பண்ணீங்க. என்ன லிங்க் உங்களுக்கு அனுப்பிச்சோம் அந்த இல்ல ஒரே அது பார்ட்டிசிபென்ட் எல்லாருக்கும் கொடுத்ததுனால எல்லாரும் உங்களுக்கு வந்து ஸ்ரீராம் ராமசாமி இருக்காது எனக்கு. ஸ்ரீராம் ஜாயின் ஐடி நம்பர் நீங்க உள்ள வந்துட்டீங்களா சார்? இப்போ நீங்க ஜாயின் பண்ணுறீங்க. ஒரு நிமிஷம் உங்களை வந்து ஹோஸ்ட் ஆகும். சார் என்ன நேம்ல இருக்கு? ஸ்ரீராம்
வருதுங்களா?
ஓகே ஓகே. உங்களை வந்து கோஹோஸ்ட் பண்றேன் சார்.
நீ என்ன சொல்றாங்கன்னு எழுதி வச்சுக்கோங்க.
என்ன சொன்னாலும் பாயிண்ட் பை பாயிண்ட் வச்சுக்கோ. Yeah, very good morning to all. Okay. So I'll request all the participants to kindly mute yourself, and also I request you to turn off your video, please, so that we have a very good session today. So first of all, I would like to welcome Dr. B. Manoharan, Chairman of St.Joseph College of Engineering, and the Managing Director, Mrs. B. Jessipriya, Director, Mr. B. Shashishekar, our beloved Principal, Mr. Vadisheshari Rao, and Dean Research, Dr. B. Parvadavadan. Most importantly, I welcome Dr. Ramasamy Raju, today's speaker. Welcome, sir. And also, I extend my welcome to all the participants and colleagues. So, before getting into the today's session, I would like to highlight a small virtual tool of our so since if we have conducted our this faculty development program in our college, you might have witnessed about our college infrastructure and facility. Since we couldn't do that, so I'll just briefly tell about our college and then initiate this session. Our college is St.Joseph College of Engineering, located at Oimar, Chennai. And our college started in 1994. And till now, we have 26 years of excellence in the education industry. And apart from that, we have a very good academic record, as well as we have an excellent placement record too. And recently, our college accredited with A plus grade from the by NAC committee. And apart from that, most of the courses are NBA accredited. And the infrastructure facility, if you see the infrastructure facility, we have a very good administrative block. This is our administrative block. And we have a very good classroom blocks as well as the laboratory blocks with the great ambience. And we have a very good indoor and outdoor auditorium. And we have an excellent library environment, as well as we have a very good miss hall. It can accommodate a huge number at a time, as well as we have a very good transport facility throughout Chennai. So with this note, I'll give a small introduction to Dr. Ramasamy Raju and hand over the session to him. So most importantly, the program is on faculty development program on recent trends in material frontiers. The importance of material science in the development of science and technology can be understood from the number of research group who's working on it. But still, we have a great opportunity, great number of problems and opportunities awaiting in the field of materials research. I hope these 4 sessions in these 2 days will surely enlighten the research activities of all the participants. I believe we are going to have a wonderful session. And today's session is fourth state of matter and its applications by Dr. Ramasamy Raju. So Dr. Ramasamy Raju obtained his PhD degree from Bharatiyar University and University of Freiburg, Germany. Since he pursued part of his PhD program, through the DAT fellowship, and due to this, he obtained his PhD degree was awarded by Bharatiyar University and partly by University of Freiburg, Germany. He joined as a visiting research fellow in the Department of Electrical Engineering, Kyushu Institute of Technology, Japan, in the year 2000 to 2002. Later, he joined as a development engineer in AD Plasma Technology, Hiroshima, Japan. He served there between 2002 to 2007. Later, he joined as a research associate in the Center for Plasma Materials Interaction, Department of Nuclear Plasma and Radiological Engineering at the University of Illinois, USA. He served there between 2007 to 2009. Later, he joined as a lead process engineer in Sunlight Corporation, USA, and he served there from between 2009 to 2011. Later, he served in as a senior dry etch R&D engineer in Micron Technology from 2011 to 2015. Now, currently, he is working as a senior R&D scientist in Intel Corporation from 2015 till date. He has a very good research record. He has a very good process skills. His process skills includes plasma process such as plasma surface treatment, plasma etching, plasma deposition, and abatement techniques. He also have a very good equipment knowledge in various equipments like UV visible NIR spectrometer, AFM, StarUp, XPS, XRD, etc. And apart from that, he has a very good knowledge in the data analysis tools like DFMEA, PFMEA, APQP control plan, etc. And he has published several articles in highly reputed journals. And apart from that, he presented in many national and international conferences. Also, he have 4 PCT patent application filed, one of which issued in 5 different countries like Europe, Japan, Canada, Korea, and China. Apart from that, he have 3 US patents issued and 4 US patents pending. So with this very short introduction, I'll hand over the session to Dr. Ramaswamy Raju to deliver his lecture. Thank you. We welcome you, sir. Now you can carry on.
Thank you very much. And thank you very much for the nice introduction. And let me share the screen now. So, able to see my screen?
Yes, sir. It's clear, sir.
Okay, good. That's good. Just give me a second. So all these things which is coming in the side. Just give me a second. I'm trying to no. Okay, good.
So you can share the screen. Yeah. But when I say share screen, it is going to be your screen.
Okay. Can you able to see my screen now?
Yes, sir.
Good. Awesome. Okay. Thank you very much for your introduction and the opportunity today to talk about fourth state of and applications. So now, we just start a little late, but I will try to, complete the presentation at the right time. So thank you very much for this opportunity. So let me go through the presentation. So the today's talk is fourth state of matter and applications. So this is the part of recent trends in material frontiers. And I will be going through the slides. The slides are not moving. Can you able to see the screen? Let me see. Okay, no problem. I found out. Okay, let me start from introducing myself. Um, I'm a dad of two kids, and currently I'm working as a senior development scientist, working at Intel Corporation in India, in USA. Sorry, I got my PhD in physics from Bardiyar University, Coimbatore, and I was a CSIR SRF fellow while I was working for my PhD, and then part of my PhD was under DAD fellowship in Germany, and also I was JSPS fellow in Japan. And after that, as a research associate, worked at the University of Illinois, Urbana-Champaign. Right now, I'm also acting as a director for Solar Shakti panels and Ramlinga Packaging Industries in Sivakasi. That is my native place. And I love Ilayaraja and A.R. Rahman's music, and I would like to read, a lot of Karisal Ilakyam. I participate in marathon and also play cricket in the United States. So before going into the talk, the current issue that we are all facing, is a corona pandemic. So I would like to, you know, I would like to pray for a minute, every one of us. Let's pray for COVID-19 victims all over the world for a minute, and then I will resume my um, presentation. Okay, thank you very much. Please stay safe. Take care of yourself and your family. So that's most important than anything else in the world. So let me go to the talk. Okay, so you all know about me now. And so Intel, an introduction of a little bit about what we are doing here. We all know that, what we are doing. Most of us knows that, Intel means, the processor. We make processors for the computers. You might have seen in your laptops, in your desktops. That's what everyone knows. So Intel is an American multinational corporation and technology company headquartered in Santa Clara, in California, actually. So Intel supplies microprocessors for computer systems that every one of us know. The one thing that some of us might not know is Intel also, working on the memory products. So computer processors are one aspect. That's what everyone knows, but Intel also does memory. So if you look at your phones or laptops or whatever the electronic devices, you have memory. So the common current data storage options are DRAM. We know that dynamic random access memory, and NAND, and then hard drive. However, we are working on revolutionary memory products at Intel that's called Intel Optane technology. So in the Intel Optane technology, I'm a plasma etch development scientist. Intel Optane, to just know more about Intel Optane, I just play a video for 2 minutes, and that will give us some more information.
When it comes to your data center, performance is everything. That is, until the cost of that performance is prohibitive. And unfortunately, that's often the case with the memory that fuels our servers' CPUs with data. And that's why hot, warm, and cold storage tiers exist, to deal with trade-offs among performance, capacity, and cost. Today, there are 3 primary technologies used to store and access data. First, there's DRAM memory, which serves as hot storage for the most frequently accessed data. DRAM's incredibly fast, but also expensive, especially at large capacities. For cold data, there are hard drives, which are orders of magnitude slower than DRAM, but very cheap and high capacity. And that's why the bulk of our data is stored there. In the warm tier, there are NAND SSDs, which are much faster than hard drives, but cheaper than DRAM. These extraordinary differences in performance, capacity, and cost between today's technologies force us to restrict hot storage capacity, resulting in big performance penalties when the data your CPU needs isn't there. 3D XPoint technology is about to completely rewrite the rules governing the hot, warm, cold storage pyramid. Why? Because it's nearly as fast as DRAM, while its cost is much closer to NAND SSDs. Intel is designing both DIMM and SSD solutions with 3D XPoint technology. Intel DIMMs based on 3D XPoint technology will enable you to greatly expand your high-performance hot storage capacity without breaking the bank, unleashing new levels of performance and responsiveness for the apps and services that power your business. And Intel Optane SSDs, based on 3D XPoint technology and other Intel storage innovations, will enable much faster warm storage. Plus, Intel has already introduced 3D NAND technology into SSDs, boosting density and increasing the capacity of those drives. These new Intel SSD technologies can expand warm storage capacity with excellent performance and cost. So get ready for outstanding cost-effective data center performance with the latest breakthrough memory innovations from Intel.
Thank you. So right now I will go to my presentation. Just give me a second, please. Okay.
So I'd now like to move to a new technology
Oh, no.
that we're excited about as well. And that's computer architecture, right? We're all here because of computer architecture.
Okay, sorry for the interruption. Looks like there is something something wrong with the network. Okay, anyways, I'm back, and so hope you guys all enjoyed the video. So basically, in Intel, we are working on this new memory technology called Optane. That's where I'm part of the Plasma Etch development scientist. So now, I'm moving to the presentation right now here. So we all know that the three states of matters. The one is solid, and another is liquid and gas. So just an example, you have ice cube that's solid, and when you heat it up slightly, a little bit, you will see, it started melting and it become a liquid. And then when you add more heat into it, it will become a stream. So basically, these are the three states of matter. We already know about it. And we studied in high school and sometimes in the first year of the college. So there is another state called the fourth state of matter. That is, so when you have solid, right? So let's say the example is an ice where the temperature is at 0 degrees centigrade. If you look at the molecules are fixed in the lattice. And, if you look at the liquid, the temperature is slightly higher, between 0 to 100, where the molecules are free to move. But if you go to the gas, when the temperature is greater than 100 degrees centigrade, so what you see is, the molecules are free to move in a large spacing. And then when you add up more heat into the gas, we'll go to the state where it's called ionized gas. So when it become more harder, so what will happen is, let's say the hydrogen will become hydrogen plus, and then two electrons. So this is in the ionized state of the gas. So basically, in this state, ions and electrons are more independently large spacing, and you have electrons, ions, and molecules. So basically, if you look at this, this is solid. You have a definite structures, and in the plasma, you have these charged particles and neutral particles like molecules. Those are all moving randomly inside the plasma. So basically, when you want to create a plasma, so you have to start adding energy, either in terms of heat or in terms of electrical energy or whatever, into the solid or gas. You will end up getting plasma. So this is a very simple example, even though it looks like a cartoon of a high school level, but still it explains what plasma is. So my objective here is to give a kind of clear understanding of what plasma is, and start with how you understand the plasma and what are the definitions of plasma, and then go to the application side. Okay, let me go to the next slide. So this is again another example of fourth state of matter. So you have a solid rock, and then the water, and then the clouds are gas, and then you have a lightning that is the plasma. So lightnings are in the plasma state, where you see you see that it's kind of arc. It's a kind of arc discharge. So this is basically at the ionized state. So let's go to a practical definition. So instead of going into more scientific definition, let's say if someone don't know about plasma, right? So the easiest way to define plasma is the fourth state of matter. In plasma, the electrons are unbound from the nuclei due to very high temperatures or large voltage potentials. So this will give us a layman to understand what plasma is. And then if you go to the next slide, this slide will tell us how the electrical conductivity is different between gas and plasma. We know that gas has molecules, however, plasma has ions, electrons, and neutrals. So definitely electrical conductivity of plasma is extremely higher. And if you look at the velocity distribution, the gas is usually in a thermodynamic equilibrium. However, in plasma, individual particles can have widely different speeds because electrons, ions have different mass. We know that electrons are really tiny compared to ions, and you have a neutral particles. So those three particles have different velocity distributions, different speeds. So basically, if you look at the interactions in the gas, right, we have one-on-one collisions in the gas between the molecules. In plasma, each particles are constantly interacting with electric and magnetic fields over long distances. So plasma itself have its own electric and magnetic fields because you have charged particles. So the commonality is neither gas or nor plasma have definite form or volume. So moving to the next slide, again, I'm just going to the fundamentals right now to make sure that the audience get what plasma is, how you can differentiate plasma with other three matters like solid, liquid, and gases. So if you look at the solid, so we all know that condensed matter and it's very compact. There's a definite shape, and it fall under nuclear natural system. So liquids and gases, they follow fluid systems, they follow the Navier-Stokes equations, all those sorts. So the plasmas basically, as I said, plasma has charged particles, electrons, ions, and then neutral particles as well. So it follows the Maxwell-Boltzmann system because it's the electromagnetic system. So now let's go to after looking all this, now I can go to the standard definition of plasma. So plasma is the fourth state of matter that we already discussed, where the material has become so hot that electrons are no longer bound to the nuclei. Thus, plasma is electrically conducting. So it has a collective behavior. So sometimes it behaves as a liquid, sometimes it behaves as a gas, sometimes it has a electromagnetic type of behaviors. So depending on the plasma type and depending on the plasma characteristics, it behaves in a different ways. So simply, in other words, a plasma is an ionized gas where you have ions, electrons, and neutral particles in an equal amount. Sometimes, we call plasma as a quasi-neutral gas. So it maintains the quasi-neutrality. What does quasi-neutrality means is it typically have equal number of ions, electrons, and neutral particles. So one thing to make sure that audience, plasma physics in the plasma in physics not to be confused with blood plasma. Those two are two different things. So now we know what is plasma. Now let's go and talk something interesting. So every one of us, right now, wherever we live, the universe, right, the earth, it's really a smaller percentage of the universe where we are living right now. So in reality, 99% of the universe is made of plasma. So plasma is the most common form of matter in the universe. So the astrophysicist often says that it's the first state of matter. The reason being, this is the first matter formed immediately after the Big Bang theory. So let's go to quiz. So I'm not going to ask you to answer the question. I know that all you guys are muted. So we have plasmas in daily life as well. So I said 99% of the universe is made of plasma. That is one thing. And we have some, or I would say very few items you have in your home or in your lab or in your office. You might have seen some of the plasmas. some form of plasmas on the way when you are walking in the street in a busy, industrial area. You might have seen some of those, but I will just go through one by one. So the plasma TV, I'm pretty sure some of us might have plasma TV at home, and the fluorescent lamps, the lamps at our home, the fluorescent lamp, it's a discharge tube basically. So you have plasma inside. But you may ask a question, plasma, you are saying that plasma is so hot, but I never felt, that hot when I go closer to the fluorescent lamp. Yes. So that's because the specific heat capacity of the electron that is not making. So when you say temperature of plasma, it often says temperature of the electron. So the temperature of the electron is like 2 electron volts, 3 electron volts, depending on the type of plasma. So fluorescent lamp, we all might have at our home. And neon signs you might have seen in our malls, busy towns. You might have seen those neon signs. And lightning, so minnal. So this one you might have seen so many times in your life. That is a plasma. And then welding arc, you might have seen in your the workshop in your college. Technician might be working with the TIG welding, arc welding kind of things. Those are all plasmas. And then the sun, the biggest one, which is giving a lot of energy and power to us, is the sun. Sun is actually the biggest star, which is made of plasma. And then all the stars are plasma. And then some of the electrical engineers might have seen the Tesla coil in their lab making some weird noise and creating some kind of sparks. Those are all plasmas. Okay, so natural occurrence of plasma. So where we have plasmas, why 99% of the universe is made of plasma? Yes, at about 80 kilometers above the Earth's surface, everything is plasma. The atmosphere is no longer made of gas. Instead, it's made of a plasma. So these are the examples. So the stars, sun, solar wind. We know that the solar wind is high energy electron beams, and interstellar space between planets, star systems, and galaxies, lightning, auroras, and ionosphere. But one thing, the closer to the home, on the other hand, plasmas are rare occurrence, except if you have a plasma TV or plasma display in your refrigerator, or if you have fluorescent lamps, neon signs, you might be seeing plasmas every day. Okay, plasma characteristics. So the plasma is so we already know that we discussed that plasma have protons, electrons, they have equal number, so it's electrically neutral. That means Ni, the density of ions is approximately equal to density of ions and density of neutrons. Okay, so the plasma is freely flowing. So plasmas are affected by electric and magnetic fields. You can bend the plasma as you like. You can shape into you can shape into any kind of shape, different kinds of shapes, because it will interact with electric and magnetic fields. If you apply a magnetic field from outside into your plasma, you will see how the plasma is changing. So there is a big application. The whole world is looking for something I will talk in few slides later. So that actually uses huge magnetic fields to confine the plasma. See, it's very difficult to confine the plasma, but there are research going on there and very interesting research. So basically, there in the plasmas, we have two different types. You have thermal plasmas and non-thermal plasmas. So thermal plasmas, the characteristics are the electron and ion temperature are equal. And in non-thermal, electron temperatures are always larger than the ion temperature. Okay, now if you look at the plasma characteristics, what you are seeing here, so the electron temperature and the gas temperature, wherever you see the difference, those plasmas are non-equilibrium plasmas that you can create in the lab. And thermal plasmas, yes, you can also create this in the lab. The arc welding is a thermal plasma. and you have this is something you can just characterize the plasma or the electron temperature. This is the temperature of the electrons versus the pressure regime where you create the plasmas. Okay, this one is interesting one. The plasma density in the y-axis and the electron temperature in the x-axis. So whatever we discussed, right? The solar wind, solar corona, and ionosphere and interstellar, all these things. You see here, it has a different plasma densities. So ionosphere have less plasma densities compared to the plasmas where you create in the lab. This is called process plasma. Look at the fusion plasmas, where you do a nuclear fusion, nuclear reactors. They actually run at a very high density, lot of it's really high energy plasma right there. So fusion reactor is right here. So the interstellar area gas, the area, that's where we have a less plasma density, and then solar wind is the next one. Okay, so when we go to the different types of plasma here, we are all scientists and engineers. Some of us might have have heard about this. DC magnetrons for making a thin films, that uses plasmas, and DC arc for the arc welding uses plasmas, as you see here. So this is the frequency of the power source that used to generate the plasmas. Usually most of them are in the RF region. Some of them are in the microwave region that you see ECR plasma, that is electron cyclotron resonance plasma, and surface wave plasmas. So basically, this one slide will tell us what are the different plasmas we have and what are the different densities, regimes, or electron temperatures plasma we can work in the lab or in the fusion reactors, so on and so forth. Okay, let me simply explain how one can generate a plasma. So now so far we talked about the natural occurrence of plasma for quite a long time. Now I'm jumping into how one can generate plasma in the lab. It's not going to be very complicated. I will explain in a simplest way. So what we need is two electrodes. One is cathode and another is anode. So what we do is we power up this cathode with RF or DC or microwave, whatever the plasma that we want. The most important thing is before you power up, you have to pump this down. So meaning, you have to use a vacuum pumps to bring this, chamber into vacuum. So typically, the man-made plasmas are 10 to 100 milliliter pressure regime. So when you apply the power to the electrodes, between the electrodes, of course. So what you see is, so at the beginning, right, you are at the vacuum level, right? And then you have molecules. So you have electrons. The first electron started coming out. It may be coming out from the electrode, or it will be coming from inside the chamber. It just hit the molecule, and then that will knock out the electrons, and then that electron will start hitting the neighboring molecule, and then start hitting, start producing electrons. This will happen in a fraction of millisecond or so. You started seeing plasma. So for creating plasma in the lab, what you need basically is a plasma chamber, a conducting chamber, and you need a power supply, you need electrodes, and then you need gas. Absolutely, you need a gas to create a plasma. If you don't have a gas inside, sometimes it creates nitrogen plasma inside, but it's very difficult to stabilize. So look at this, the ionization potential for different gases. So most common plasma people make is argon, krypton, and some of the applications people make helium. So so depending on the ionization potential of the gas. So ionization potential is something, the potential required to knock out an electron from your molecule, right? So it's easy to make plasma when your ionization potential is lower. For helium, maybe you need to give more power, Instead of giving 500 watt, for argon, you may need to give a little more power. Okay, now we know how to create a plasma in the lab. Okay, good. Okay, plasmas are colorful. Okay, I will be showing some pictures, but I will hit the applications point of view. Look at this helium plasma. Every plasma have different colors, different characteristics. That is because of different wavelengths. Um, so it emits the light after making the plasma. So look at the helium, neon, argon, xenon, krypton, mercury vapor, and then the H2. This is a kind of neon sign we might have seen in the mall. If you go to Phoenix Mall or Forum Mall, you will see this, some of this. So the application of plasma started right now. Number one is lightings. That is something we typically use in our daily life, and we see that every day. Okay. Next one, the big one, is the fusion. Okay, how plasmas are the important part for the nuclear reactors. Without plasma, you cannot create fusion reaction inside the reactor. So let me just start from the sun. We all know that. We have studied that in our high school, in our physics subject in the first year of engineering. So what is fusion? Well, light atoms like hydrogen can fuse together so tightly, and then they release the energy. Yes. So it's tremendous amount of energy. So when that happens, because two positively charged nuclei get close enough, that fusion will happen. Okay, so in the sun, how the fusion is happening? Because the sun's core is a natural fusion reactor. So before sun is formed, it is a cloud of gas, mostly made up of hydrogen and helium. So you have hydrogen and helium in the sun, and we all know that sun is at very high temperature, and we expect numerous collisions are happening, and we have a plasma there. So the fusion starts there in the sun, because it begins in the sun when collision between ions becomes so frequent, so that the ions get close enough to fuse together. So the sun, how that reaction is happening is very, we all know that. So we are actually, the hydrogen atoms becoming helium, and then it's actually converting a lot more energy. So this is just a simple equation. We all have that in our physics book. So the amount of energy that we get, the output of the sun is closer to 4 times 10 to the power of 23 kilowatt. Yes, though every second, it's happening in every second. So a lot of energy, that's why a lot of light, we are getting, the stars are getting energized. So it's tremendous amount of energy. Okay, so now the same principle, right? You have a plasma there in the sun. Mute this one. Okay. So can you able to hear me, right? Hello, Dr. Suresh, can you able to hear me? Okay, awesome. Yeah, thank you. So right now on the Earth, scientists are trying to build a fusion reactor on their own. Now apply the same, principle. What is happening in the sun? But can you create a lot of sun in the lab? Can you make like it's very tough. But people are doing it. The scientists are building the nuclear reactors, and they are actually creating a hydrogen plasma, and they are trying to fuse the ions and making the fusion happening in a controllable manner. So that's where the plasma is playing a role. So in the sun, you have plasmas and you have ions there. So wherever you have ions, where that's the area we have to fuse the atoms together to make uh, energy. So basically, in order to basically they try to get atoms close enough. How they are doing it is maximizing the number of ions in the smaller region. So to have more ions in the specific region, we need to have a plasma in a shorter time. So basically, fusion reactors are working with that principle. If you look at it, so this is the plasma fusion in the Earth, where this is the tokamak plasma fusion reactor at Princeton Plasma Lab in USA, and then plasma fusion reactor at MIT. They are all actively working. You know why they are working? Because they think that it produces tremendous amount of energy, and that can be used for powering your convert that energy to electrical energy, and then bring that to us, bring that to our home. That's the whole idea. So India definitely need that, because we have power cuts. We do have, even though we have pretty good nuclear, reactors, nuclear fission reactors, but people are still working on nuclear fusion. So one of the institute called Institute for Plasma Research in India is popular for building those reactors. This institute was actually developed during um, uh, 1980s, I guess, in the mid 80s. Maybe I'm wrong, but I still remember it's around 80s. So this is the Aditya, is the first Indian plasma fusion reactor they built, and then there is a SST. It's called Steady State Superconducting Plasma Fusion Reactor. So they are actively working on it. So one good thing about this institute, I would like to share some information for students if they want to. So they have a summer programs every year. They hire people from all over India. So if someone really interested to play with plasmas, they can apply for it. And they also hire a lot of new engineers every year, because a lot of challenges here, a lot of material challenges. How would you build this? You see the magnetic coils around it. It's actually with high temperature plasma, material handling is very, very hard in this one. When you work on the high temperatures, you need to have a very innovative, smart materials to handle the fusion reaction. Okay, good. So now I'm jumping into, I started with the energy. So far we saw lightings, and then the energy, nuclear reactors, you saw that. And the next one I'm going is plasma and microelectronics. This is what something I have been working recently. But I worked on a little bit on the fusion side in the past. I also worked on some of the other areas as well. But this is something in the microelectronics fabrication. The thin film deposition, right? Using PVD and chemical vapor deposition called CVD, and then the plasma etch, plasma cleaning, and then the lithography. These are the key things that any semiconductor industry or the microelectronics industry use, where there are a lot of plasma applications. Okay, the plasma etch, that is one of them I want to start. So what plasma etch does is basically, plasma etch, if you in a simple way, what it does, it removes the unwanted things. It removes the films. So it removes the stubs by chemical reactions and also the physical means, that is ion bombardment. So we know that the plasma have neutral particles that actually helps. That's called radicals. That actually helps chemical reactions. And the ions, we have ions, so the ion bombardment. So if you look at it, so what we are doing is, in the microelectronics, we are actually making a feature of nanometer. Okay, so I want to etch away in a micron level and nanometer level. So for that, the plasmas are very useful. It will make nano level trenches into your substrate. So that's where we build transistors and all those electrical things. So this is one of the models. Just look at it. So just think that you are etching a silicon, okay, SiO2, silicon wafer. Just to assume whatever you think it's SiO2, and then you have a plasma which is made of CF4, for example. So CF4, using your CF4, you are making a plasma, and you have C and F. No, it will eventually it will you get ions and neutrals and electrons. So you have fluorine ions and also fluorine molecules and CF, all those things. So those are all the you know the those are all help on chemical reactions. And then you have ions. So the ion assisted reaction is happening here, and then it will etch away the particle. So if you look at silicon, SiO2, and then you have fluorine. So it started, hitting the surface and etching away. So while it's etching away, basically when it goes, it's absorption mechanism when the radicals go in and sitting on the surface where we wanted to remove, and then the desorption. So at the desorption, if you look at the silicon, you are using a fluorine gas. So what you get is SiF. So silicon fluoride will be pumped out from your vacuum chamber. So basically you will be etching a very, very small nanometer scale. The nanotechnology needs, every electrical devices needs to get smaller, and it has to work in a very fast rate. So people are really trying to make a smaller features. So I just, this is one of my patterns. If you want to just go through and see it, you can see it. There is nothing secret about that. So so plasma etching, right? We make, so see one of these examples. Look at this. This one is 43 nanometer, and this is 28 nanometers, and this is 19 nanometer. Of course, we are making even smaller than this. The plasma helps, make a smaller. You need to make really tiny, really small, so that you can build transistors, you can build the electrical devices. When you look at the processor, or when you look at the memory chips, oh, tons of transistors, tons of electrical components in there. So we need to build those using these techniques, plasma etching, plasma depositions, and all those things helps us to do some good work over there. Okay, so I'm moving to the next one. Okay, so far we talked about etching, a little bit of etching. What is etching and all? So the etching, if you talk about the etching, we use different types of plasmas. One is the inductively coupled plasma. So in a simple words, right, you have a chamber right here, you have a silicon wafer right here. You will be powering up these coils. So these coils will inductively couple to the gas, low pressure gas inside the plasma, and generate the plasmas. The mechanism is same. So one electron will start and keep going and make ionizations like that. So this is just a simple diagram of ICP etcher, inductively coupled plasma, where you have an inductively coupled coil, and there is a dielectric window, and you have a plasma chamber. So you power up with RF generator, and there's a bias generator as well to pull more ions and make your plasma etch more effective. So these kind of etches are used in our industrial applications. And the another type is electron cyclotron resonance. So basically what you are doing is you are feeding a microwave. So far we saw RF power. So you are feeding a microwave through waveguide, and you are actually having a magnets right here. So what this magnet does is look at this, the DC magnetic field, the electron cyclotron, this is the equation QB by M. So the electrons accelerated if this frequency matches with the microwave frequency. So microwave frequency is 2.45 gigahertz. When we match that frequency, what it does is it actually accelerates the electrons so fast. So when you accelerate the electrons so fast, what it does, it's actually hit the molecules on the way and make more ionization. That means you get more electrons, more electron density and high density plasma. That's what it does. So you get high dense plasma, meaning high electron density, and that is much desirable for many applications. So going to the next one. So ECR and ICP. What is the difference between ECR and ICP? As you see, this uses microwave and this one uses the RF power. So we know that this works under the principle of electron cyclotron resonance, and this is inductively coupled principle. And this one is a high density plasma compared to inductively coupled plasma. So depending on the application, people use different types of plasmas. Okay, starting from DC or ICP, CCP, and electron cyclotron resonance. So we saw, so far we discussed, okay, what is plasma, and how do you define the plasma, how that plasma is different from other three states of matter, and where are all you see the plasmas, and the natural existence, and the characteristics of plasma. And we also see applications, lighting, and we also looked at the fusion in the energy, and then the plasma etching in the microelectronics. And also we saw different configurations of plasma reactors. Of course, we discussed about how plasma is generated in the lab. Good. I'm jumping into the next application that is more of thin films. Okay, in the thin films, PVD. So one of the PVD is the sputtering. Sputtering, of course, have RF, DC. You have a high pulsing, various different configurations of magnetron as well. So we all know. Some of us might have worked on this. It's a vacuum chamber where you are creating a plasma here, where you have your sputter target. Okay, you have a magnetron sputtering. You see the magnetic fields around. So you see the plasma, right? This is the target where you want the material to be deposited, right? So what you target in the sense, the material target, not the substrate. Okay, so you make a plasma here. So when you make a plasma, what happens is let's say you are making argon plasma, and the argon ions, started bombarding your substrate and knocking off the atoms, and then that atoms are going here and depositing here. So there are so much of films, metal films, dielectric films, the silicon oxide, titanium oxide, a lot of solar applications like ITO and zinc oxide. Nowadays, sputtering becomes so versatile, and it can be used anywhere, any industry. So this is one of the, when I was working for solar, right? So this is one of the flexible solar panels that we made. This really, you can just, it's very flexible. You can just fold it, and then you can keep it in a backpack. And so this is something, if you are interested, you can just go and look at some other patterns where I used, magneton sputtering for making solar cell. Okay, the application into nanoscience. I know that some of the professors in chemistry and physics are actively working on some of the nanoscience research at your college. So see, the DC plasma, CVD, is very popular. You see this C2H2NH3 plasma. is creating a beautiful, carbon nanotubes. And this RF plasma with C2H2 and NH3 is creating really dense, the carbon nanotubes. This is one of the examples. And then the atmospheric pressure plasma. Okay, here I need to talk a little bit more, because so far I said if you want to create a plasma, you need a vacuum chamber, you need to create low pressure, so on and so forth. Of course, you can create plasma in the atmosphere also. This is something really new for the last, maybe I would say 10, 15 years. A lot of people are working on it because you don't need an expensive, vacuum pumps and chambers, because you need chambers depending on the application, of course. However, you don't need a vacuum, expensive vacuum pumps, exhaust and all those things. So this is one of the atmospheric pressure plasma where you see the carbon nanotube is deposited here. This is one of the examples where you create a plasma in an atmosphere. You just flow the gas and you have a temperature to substrate monitoring your temperature heaters. So you actually generate a plasma in between, and then you create carbon nanotubes. Okay, so here the another example of making something interesting stuff is using this atmospheric prosoplasma. You make the nanostructures. It's very simple. It's a small tube. Look at this 100 micron tube, capillary tube, and you flow this argon silane gas, and you actually treat with the plasma, and you started getting nanoparticles. So this one is fluorescent silicon nanoparticle. So atmospheric prosoplasma is something very interesting for nanoscience people, because they can even have the tool easily. It's cheaper compared to your plasma that you create in a vacuum. Right? So the plasma spray coatings. This is also atmospheric prosoplasma. I think some of us might have seen this either in your college or in your foundry, or somewhere when you went for internship or something, you might have seen this. So this is a protective coatings for high temperature, corrosive resistance, lot more applications, of course. Even it has application in the medical, the hip implant, titanium oxide coating, and textile parts, titanium oxide. This is something, look at this, the turbine nozzle. It's actually eroded, and then after coating, how it looks like. Okay, I think I'm taking time, so I have a few more slides only. So plasma surface modification. Look at this. Look at these parts. It's inside the plasma chamber. What exactly they are doing here is changing the surface. They are actually making it more harder and making the life longer. They make a nitrogen plasma, and nitrogen ions will be, implanted inside. Instead of saying implanted, let's say impregnating. So basically, in the surface level, maybe like several angstroms or nanometer level, your surface will get more harder because of nitrating. Look at this beautiful picture where you have something shaft or something inside the plasma. Okay, so they do nitrating, they do carburizing, then make the surfaces harder. Okay, I'm just going to show one of my inventions. So when atmospheric pressure plasma was so popular, so in early 2000s, there were really very, you can say very less or seldom atmospheric pressure plasmas in the market. So this is one of them that I have a patent on it. This is the one, the patent issued in several different countries. Look at this. People are touching the plasma. So this is a kind of application. It's called, nowadays people are calling this as a cold plasma or cool plasma. Why it is cool or cold? Because it's cool, first of all, you see somebody is touching there, and the temperature is low. The gas temperature is like, 50 degrees centigrade, 100 degrees centigrade, even a little more, depending on how much power you give. So this is one of the invention I want to show what we did with this. Okay, sorry, this video, I just checked it, it did work, but I will go to the results. Okay, I used this for surface treatments. So we know that a lot of issues with wetting, changing the wettability of the surfaces, make your surfaces more hydrophobic or hydrophilic. So this is one of the samples from top automobile company. They gave us a secret material to treat with plasma. Look at this with zero point 0.5 seconds of treatment time. You see the contact angle. Contact angle, how you say is, if your surface is really hydrophilic, when you just put a droplet there, you see something very nice, safe, like shape like this. And the contact angle is always bigger. And when you treat with plasma, you'll see it will be very flat. So that's where you get zero contact angle degree. So this is one of the applications that we used. So this is interesting because this actually happens. I'm sorry that the video didn't work, but look at this. What happened was when we are working on this project, there was a secretary in the lab. We are just showing her that, hey, see a cool plasma. It looks nice, beautiful color. Do you want to touch it? And she said that, yeah, if the temperature is not that high, I would like to touch it. And then she just touched it. Of course, she was, exposing the plasma for about maybe like 20, 30 seconds. After that, she said, oh, it's hot. So what happened was, next day she came. Next day, she came to our cubes and she was telling that, hey, yesterday, I actually had a small cut on my surface and a small boo-boo. But I feel like after, having this 20 seconds of exposure yesterday, I feel like I feel better. It looks like it's healing something. So that was the spark, actually. So what we did was, we started getting bacteria samples, right? The E. coli bacteria from the lab, from the nearby hospital and the labs. Look at this. Before you expose to plasma, you clearly see how dense the bacteria is. 5 seconds killed almost all of them. And in 30 seconds, completely, everything is gone. So you see here, this is the bacterial density, right? It's like 5,000, 6,000, and then it dropped down to 0. So it was actually an accidental thing that happened. This is one of the patterns, of course. If you are interested, you can go and check it. So what we did was, after this, this picture looks really awkward. Sorry to show this, but this one, we have a commercial plasma system, which is actually treating a chronic wound in the hospitals. Look at this before and after treatments. I want to go faster because it looks awkward. Okay, now look at this. Based on the concept, we actually made different plasma sources, like hand cleaner and nanoplaster. Let's say you have something here, I want to treat it. You can use it. And this is a personal plaster. You can keep it in your bag. But really, do we need to treat this with plasma? People really worry about, you are using electric fields, microwaves, this and that. Really? Can you, is it really works well? Well, it's working right now. Of course, there are some concerns, if you have higher power, higher things, it may end up getting some shocks, but it's commercialized and people are using it. Now, I'm coming to the end. Okay, now it's the corona pandemic, right? So people are actively looking plasma sterilization for corona applications, not killing the corona bacteria, but I'm pretty sure plasma will kill the corona bacteria. But you have a bacteria inside your body, so you cannot put your plasma torch inside. like someone said, we can have a Clorox inside. That's a funny story. But so basically, plasma sterilization can help outside. So you can use for cleaning your masks, gowns, and reuse them. So already, some people started looking at it. The University of Michigan in USA, they have been started using it. Okay, I'm at the last slide. So I would like to thank my friend, Dr. Punita. She's actually initiating all these efforts. She have been telling me a couple of times. So finally, I got a chance. Thank you, Punita, for the opportunity. And thank you very much, Dr. Suresh and Saravanan, for all your help. You know, I really appreciate you guys, doing the things in a systematic way, checking all this, connections and slides and everything. And, started checking time ahead of the presentation and all those things. Thank you very much for the opportunity. And once again, I apologize for some of the issues with the media at the beginning, where we had some noise and all those things. I'm sorry for that, but this is this is something, common thing that we always see in the webinars. But that's something. The end of my presentation. I really appreciate all of you for your time. I'm not sure I took a little more time today, but sorry for that. But, this is something worth talking about.
Thank you, sir. Thank you so much, sir. Now, can you answer the questions in chat box, sir? If anyone chat now.
Oh, absolutely, yeah.
Yeah. If anybody post any question, you can answer kindly if possible.
So the question is, Suresh.
I request all the participants to post your question now. If you have any questions, you can ask.
No questions, really?
Sir, so I have a doubt, sir.
Oh, sure.
So you said that plasma. Okay, generally what we know is plasma is very high temperature, right? But you're saying that plasma can be treated on human being to cure diseases, to kill germs, etc. So how is this possible, sir? If this same plasma, if we say the plasma is very high temperature, but here also we are using the same word plasma, or any other terminology is there?
Well, yeah, plasmas are definitely plasmas are defined as high temperature ones. But this is something new in the atmospheric pressure side, right? So it uses really a low power, really low power with high gas flows. So what you see there is you will not see the quasi-neutrality. You will not see the number of electrons and ions and neutral particles are in equal number in those cool plasmas. This is a new types of plasmas. Still, that is categorized as a plasma. So what you see as a temperature is the the neutral gas temperature. So on those plasmas, as I said, we use really low power regimes and high gas flow that actually make the neutral gas temperature to be lower. So if you look at one of the examples in the nanoscience example, the mycroplasma, that is actually a very tiny plasma. So you will not feel that hot. But when you see the fusion reactors, it's definitely a hot plasma. So that's why I explained in the beginning, non-thermal plasmas and thermal plasmas. Typically thermal plasmas are really hot, and non-thermal plasmas, especially if, come under the category of atmospheric plasmas, where the number of electrons, number of ions, and the neutrals are not equal. So where you see lower temperature, that's a pretty new applications coming up right now.
Fine, sir. Sir, few questions have been posted earlier. Sir, shall I read that to you, sir?
Oh, please. Is it under?
Yeah. Is there any possibility to make a thin film plasma coating on face mask and wearing glass?
Yes,
Is there any?
absolutely. A lot of people use, I mean, a lot of plasma coatings, especially the plasma coatings using the sputter deposition that I showed, one of the examples, they are using it for the optical glasses. More than optical glasses, I would say the structural, the buildings, right? The structural glasses are completely solar glasses, solar coatings. All those things are possible with the with the plasma deposition for sure. And the another question that you asked was the face mask, right?
Yes, sir. Face mask.
So yes, absolutely. People are actually doing it. They're using the low temperature atmospheric plasma. Trying to make coatings on different surfaces. They are even making on Teflon. Even they are making on the flexible substrates. So it's highly possible with the current plasma technology. You can have coatings on any material because you have a low temperature plasma available in the market. That is highly possible. Yes.
Another question, sir.
Yeah.
How can we control the avalanche effect of electrons in plasma generator?
Avalanche effect. Yeah, that's a good question. I mean, so in atmospheric in a vacuum plasmas, well, the avalanche effect eventually, um, it start with an electron, and you saw, the cascading of electron bombarding with the molecules happening. So at one point of time, right, you are in a vacuum system, you are feeding the gas as well as you are pumping down as well, right? So at one point of time, you reach the equilibrium where that's where you most probably ionized, not the 100%. You most probably reach a high ionization percentage where you reach the maximum. You reach the avalanche, but typically it happens pretty quick in vacuum plasmas, especially when you create a low pressure. That typically happen these days with all these commercial devices, right? Making smaller features and all those things in the semiconductor industry. It will happen in microseconds, milliseconds also. The tools have that kind of capability to reach that level. So once you have the avalanche, you have a stable plasma going on inside the chamber.
Fine, sir. One more question, sir. So, what
Yeah.
is phase rule linked with plasma? Is there any rule linked with plasma phase rule?
Can you repeat again? Your voice is breaking.
What is phase rule linked with plasma? Is there any phase?
Phase rule. So are you asking about what is the criteria for the plasma?
Yeah. Sir. I think they are asking that question only.
Okay. So if you talk about the criteria for plasma, as I explained, you at least have the first thing is you have a certain amount of ionization happening there. For example, flames you cannot categorize as plasma. Plasma flames also at a high temperature, right? The
Right.
burner, in industries, paper industry or some other industries, they use a lot of burners with coal and all those. Those are not plasmas actually. So,
Fine.
if you want to categorize or if you want to say a particular phase as a plasma, the major thing is, I mean, a specific percentage of ionization should happen over there. And also, you should be having electrons, ions, and neutrals, um, both in there. But for the ideal plasma, definitely the fusion plasmas and other high temperature plasmas, we typically have equal number of those. So that is the number one criteria for plasma. So how much ionization, that actually matters. And of course, there are several other things that I didn't touch. There is another parameter called debase shielding. how the shielding effect is happening in the plasma. Those are all the fundamentals of plasma physics. So basically, um, quasi-neutrality, number one, and then number two is a certain percentage of ionization. Getting 100% ionization is not possible. Let's say wherever the plasma you have at least 20-30% 30% of ionization happening, then we can say that this is a plasma. It's categorized as a plasma.
So another question: what is the state of water molecule in plasma? Plasma
Oh,
state. What is the state of water molecules in plasma state? I get they asked a question. They'll
state
go.
of water molecule in plasma. You mean when?
I think they might have asked about can we heat it? And another question just posted close to it. Okay, is it possible to cool back to get the original matter after converting to plasma? Heating using plasma.
No.
Okay, sir. So very informative, sir. Thank you.
No,
Thank you so much, sir.
I welcome more questions. Don't hesitate. Don't stop right now. If you have more questions, please.
No, sir. Everyone
Sir,
asked a very similar question.
sir, one
Okay,
more
and
question, sir. Sir, one
Yeah.
more question from
yeah.
University, Professor Dr. Anupur asking, is how safe it is use energy obtained from fusion by plasma?
Yes, it is safe. Of course, the fusion reactors. I mean, we are actually confusing a little bit here. The fission reactor that we all have, let's say in Kalpakam, or what we have in south of Kanyakumari or whatever. So they uses the radioactive materials, and the radiation is a concern. Agree. And in the fusion reactor as well, a fusion reactor also, there are some health concerns, radiations, more than radiations, the temperature, those things are there. But with the developed systems, if you look at it, I will tell you an example. In America, how much you think the energy is produced from the nuclear power? It's almost 40%. It's a big country. Just think about it. People are saying it's safe or it's not safe, something like that. America have a lot of nuclear reactors where they are producing almost 30 to 40% of their power need from the nuclear energy. And then they are actually getting coal is the second one. So in India, of course, coal is the toppest one. Of course, we have some safety concerns. However, there are a lot of research going on, related to how you can safely run the reactors and generate the power. One thing is the fission reactor that we have in India or wherever, that the amount of energy you produce with the fusion reactor, plasma fusion reactor, is so much. It's so much more than what a country need. But the problem is still people are working on it. So thank you very much, sir, for your question, and hope I answered your question.
So another question, sir. Whether plasma beam can be deflected by electromagnetic lenses?
Yes, absolutely, yes.
Fine, sir. So we had a very wonderful session, sir. Thank you so much, sir.
Thank you very much, Suresh, for organizing this. You know what? I didn't put a lot of science stuff. I don't want to put a lot of equations. I don't want to put, confuse people with, starting with complicated equations and all those things. Originally, plasma physics is supposed to start with Maxwell's equation and then go with the complicated phenomena and everything. The whole idea here is, what I want to make sure is, let people understand what is fourth state, and very fundamental level, how you define plasmas and how you generate it, what are the practical applications. So if you guys really want something really a sciencey thing, like I want hardcore plasma physics, that's also interesting. for many of the physics people. But and another thing is, I apologize that I was actually summarizing the different applications, but each and every application I can start. I can give a talk. Like, let's say if you talk about the semiconductor, I can give a full talk on only semiconductors.
Fine, sir.
And if
So
you
we
talk
welcome you to our institutions, sir. Again, in future, when you visit India, please visit our institutions, sir.
Yeah, sure.
We have some good sessions there, so that we can continuously develop our skills. Very useful talk, sir. And many of the participants, they are requesting if there is any notes or anything which we can share with them. They say that they will be. It is very useful for them, as you told. Science related they are asking if anything you can share, to me. I can share to the participants.
Absolutely, I will do that. Thank you.
Okay, sir. Thank you so much.
Thank you very much. Thank you all for listening this, and I really appreciate all your time. Thanks.
Thanks. So with this, I end this session. I thank you all the participants, and I request you to join by 2:30 for afternoon session. Thank you.
Oh, thank you.
Once again, thank you very much, sir.
Thank you. Thank you all. Bye bye.
Thank you, sir. Thank you, sir.